Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue on the discussion on filter design. For this video, I'm going to share how can we design a simple bandpass filter. I'm going to illustrate with an example how to calculate the L and C value in order to achieve a bandpass frequency response. This will be the Part 10 series discussion on filter design. I have put the playlist under the description, so please take a look on those videos if you're keen to know more about filter design. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Once again, sincere thanks for your strong support. One of the easiest ways to design a bandpass filter is to use a parallel resonator. This diagram in fact shows a parallel resonator. So from this diagram here, you can see that basically the L and C, they are connected in parallel. So this is the L, this is the C. They are called parallel because L and C is basically connected in parallel. So therefore, this in fact form a parallel resonator. Okay, one item that I want you guys to take a look is basically this RPL. Okay, so this RPL is the parallel loss resistor of inductor. Okay, which means that this resistor loss is actually contributed by the inductor. So if you see this diagram here, you can see that this is the whole chunk of inductor. Okay, besides having the inductor value, okay, we also have the resistor loss that is contributed by the inductor. So later on, I will share with you how to calculate this parallel loss resistor of inductor. And basically with this, you can actually calculate the L and also the C value, which I'm going to illustrate later on with an example. A simple bandpass filter can be designed, okay, as long as we have this following information. Okay, if we have the resistor of the source, okay, which is Rs, okay, so this is the source resistor. If we have this source resistor, and if we have the load resistor, okay, this is load resistor. If we have F1 and F2, F1 is the lower cutoff frequency, F2 is the upper cutoff frequency. Okay, so this basically determines the bandwidth. Okay, so as long as we have these two parameters, and last but not least, we have the component Q of an inductor. Okay, so when we actually purchase this inductor, okay, we actually can know the component Q from the data sheet. Okay, so this is what it means by component Q. Okay, so let's start. Okay, there are a few steps. In fact, there are 3 steps. How can we design a bandpass filter using parallel resonator? So firstly, okay, we can calculate F0, which is the resonant frequency. How can we calculate the resonant frequency? It's governed by this equation. F0 is equals to square root F1, F2, the lower cutoff frequency and the upper cutoff frequency. So from here, we can calculate the resonant frequency. Next, okay, we can also calculate the circuit Q, okay, which is the Q for the whole circuit. Okay, this is basically how we can calculate the circuit Q. So this is F0 over F2 minus F1, resonant frequency over upper cutoff frequency minus lower cutoff frequency. If not, okay, so we can also calculate the total circuit Q by this equation, which I have proved it to you early on the previous video. Okay, so this is the Q of a parallel resonator, okay, which is governed by this equation. Okay, so the total resistor, in fact, will be all these 3 resistors in parallel. So can you see here, this is the source resistor. This is the parallel loss resistor of an inductor. Okay, so this is the load in resistor. So basically, all these 3 resistors in parallel contribute the total RP. So this is how we can calculate the circuit Q. Steps number 2, okay, we can calculate the parallel loss resistor of an inductor by using this equation. Okay, so on the example, okay, I'm going to show it to you how can we calculate this parallel loss resistor of an inductor. With this, we are actually ready to calculate the value of L and C. Okay, remember this is a parallel resonator, so therefore they are governed by this equation, which I have shared to you earlier on. The total R is basically all the three resistors in parallel divided by the circuit Q. We can also do this. This is basically the resistor of an inductor itself. Okay, so remember, this is this RPL by the inductor itself. So basically, this is the component Q. Okay, of course, it's also from the inductor itself only. So basically, this you can also easily calculate what is the impedance XP here. With this, we can easily calculate the L value. If you still remember, we have discussed about this. XL is equals to 2 pi FL. So if we want to find the value of L, okay, the 2 pi F, I move it over here. So it will be XL or XP over 2 pi F naught, which is the resonant frequency. We can also find the capacitor value, okay, by using this 1 over W naught squared L. Okay, so if you're not sure how I actually got this equation, okay, you are always welcome to refer back to the playlist of filter design. Then you will be able to understand how I actually get this C value here. Okay, so if not, you can also rely on this equation to find the C value. Let's start with the example. Okay, the example tasks us to design a simple bandpass filter based on the following spec. Firstly, the frequency range is from 144 to 148 MHz. So this is the lower cutoff frequency. This is the upper cutoff frequency. F1 and F2. Okay, so the component Q, which is also given, which is 200. Okay, the source resistor and the load resistor, which is 50 ohm. Okay, so this is the typical filter input and output impedance value. Okay, so let's start. First thing, we can easily calculate the resonant frequency by using this equation, which I have shared with you earlier on from this equation here. So I can easily calculate my resonant frequency. Okay, so how can I calculate my resonant frequency? Over here, so this is F1, F2 square root. So I can calculate the resonant frequency is equal to 146 MHz. So next, I can calculate my circuit Q. If you still remember, the circuit Q formula is F0 over F2 minus F1. Can you still remember? Here, F0 over F2 minus F1. So from here, I can also calculate my circuit Q, which is 36.5. Okay, next, okay, we are ready to calculate this RPL. Okay, so this is a formula, okay, which I have shared with you earlier on. This is the formula to calculate the parallel loss resistor of an inductor. So I can calculate what is the resistor value that is contributed purely by the inductor. Okay, since I'm given the source and the load resistor are 50 ohm, so they are in parallel. So therefore, I have a total effect of resistor of 25 ohm. Okay, so this is a component Q, which is given by the question, which is 200. So this is a circuit Q that I calculate earlier on. So from here, I can calculate the resistor that is contributed by the inductor, which is 112 ohm. Next, I'm ready to calculate what is my XP. Okay, so this is basically the loss, resistor loss by the inductor itself. This is the component Q. So from here, I can calculate my XP, which is the impedance of the inductor, which is equals to 0.56 ohm. From here, I can also apply to calculate my L value and also my C value, as illustrate over here, how to calculate my L value and my C value. So from here, I calculate my inductor, which is 0.61 nanohenry, and also my capacitor, which is 1.95 nanofarad. However, I draw a conclusion. Okay, so the inductor, typically this inductor value is considered a very small value, very challenging to find this small inductor value. Typically, let's say micro, okay, will be better. Okay, however, with nano, okay, so typically this is a very difficult inductor to be fulfilled. Okay, we also have a very big capacitor value. Okay, typically capacitor is in terms of pico, for example. So therefore, with this, okay, this simple bandpass filter, okay, which is very difficult to design because we can't really find this L value and also the C value. However, let's put this into simulation, okay, because simulation we can always design with the L value and also the C value, although we can't easily find this component available, okay, we can easily simulate the result. So from the simulation result, you can see that I actually achieve a bandpass filter. So I actually have a lower cutoff frequency and upper cutoff frequency, which is by the design rule. So from here, okay, I can conclude that I done a very simple bandpass filter with the following information I need over here, which I have shown it to you. Sorry, this information here. Okay, so with this information, okay, I can easily calculate my bandpass filter response. Okay, with this, I like to end my discussion. Please help to like and subscribe. Once again, sincere thanks for your strong support. Thank you so much, guys. See you.